Hello, everybody. This is Buzz Machete at MongoDB. Welcome to today's webinar entitled Schema Design. If your travel plans today do not include exploring schema design with MongoDB, then please exit the aircraft immediately and see an agent at the gate. Otherwise, welcome aboard for about an hour. Some quick logistics before we begin. Today's webinar is going to be recorded. You'll have the video and the slides made available to you in about 24 hours. You can use the chat window for technical assistance and interactive QA. The MongoDB team is here, and they'll be monitoring that chat window and answering questions as they appear. And we'll try and save about 5 or 10 minutes at the end of the presentation today to answer the most common questions that have been submitted. All right, let's get into the thick of it. I think one of the things that's going to be very important to understand as we look at schema design today are 3 themes. You have to grasp them, and we're going to reinforce them throughout the presentation. The first is that schema design involves more than the database. I'll actually repeat that. Great schema design involves much more than the database. This isn't exactly new. It's not revolutionary to MongoDB. It's something that we've been doing all along in the construction of solutions. Sometimes we do it pretty well, sometimes not. It's just that the data structures and the APIs used by MongoDB make it much easier to satisfy especially those first 2 bullet points you see there. And as a software engineer myself, the ease and power of harmonizing your persistence layer with your code, whether that be Java or JavaScript or Perl or Python, it's a vital part of ensuring that your overall information architecture is robust. Lastly, with respect to those legacy issues, we do, at this point, need to confess that even after 40 years, RDBMS design and software integration and day 2 change still carries a lot of hurdles, like field overloading and flattening. And these are things that we've somewhat become numb to, and it's good as we take a new and fresh approach to schema design in MongoDB that we acknowledge some of those traps that we've fallen into in the past. Theme number 2, this one could be potentially a little provocative, but today's solutions need to accommodate tomorrow's needs. Now, in the old days, we had very long requirement cycles, and one or both of the following kinds of things happened. First, the requirements changed midstream, and a lot of the schema design already performed was invalidated. And this is particularly true for certain kinds of one-to-one entity relationships. Second problem was sometimes a high-quality problem, and that was the solution all of a sudden was now asked to scale well beyond the original goals. And the rally cry back then was, well, it wasn't in the requirements. And increasingly, that's no longer a rally cry that the business or, frankly, even the tech community wants to hear. Having a 6, 12, or 18-month requirements phase to build a system to last 10 years or more isn't the way we build solutions anymore. You need to get your information architecture done, your initial information architecture, done in a couple of weeks, expand upon it incrementally, and then build a system that doesn't have to live for 10 years in order to justify its development time. Theme number 3, MongoDB offers you choice. Now, because, as I alluded to before, Mongo is impedance matched, it's well harmonized with the software, this affords you a great deal of flexibility in terms of how you design both the persistent form of data and the code that manipulates it. Now, there clearly are best practices to guide you in that design, and we'll cover some of them today. But the good news is you still have ability to change course without complete rethinking of the solution. So let's get now into a little bit of the terminology. The good news is that both existing RDBMS and MongoDB have the concept of a database. Tables and collections, very similar, and in fact, you'll probably catch me accidentally saying table when I mean collection somewhere in the presentation today, because they behave largely the same way. Both have indexes. Now, where we start to get a little different is the kind of data that's held as sort of the unit. And in RDBMS, it's clearly the row. In Mongo, it is the document. And RDBMSs employ joins to stitch together fundamentally simple things into larger, more complex data. In MongoDB, we use embedding, the term embedding, of data within other pieces of data and linking to produce the same kind of result. So most of what we're going to talk about today is how embedding and linking brings together data in a way that you need to use in order to produce this complex data. So what is a document? It is not a PDF or an MS Word artifact. It is a term, document is our term, for a rich shape, as we see here. It's structures of structures with lists in it, of even more structures. At the leaves of this structure, you find the familiar scalars, like ints, doubles, date times, and strings. In this particular example, you'll see that we're also carrying a thumbnail photo in a binary byte array type. Binary types are also natively supported in MongoDB as well. Now, this overall way of describing a piece of data is very different than the traditional row-column approach used in RDBMS. Another important difference is that this document is itself the schema. The data and the types and the shape themselves form the schema. It is expected that the code layer above MongoDB is responsible for the validation of the content and the types and the overall shape. Now, the truth is, in most non-trivial systems, even with RDBMS and including with their use of stored procs, there is plenty of validation and logic that's being handled outside of the database. In MongoDB, the paradigm is that we put it all outside of the database and keep it consistent in one spot. Now, as we go forward, here's something very important. For the purposes of this webinar, you're going to be seeing this two-string representation of a document as it is emitted from our command line interface. It's easy to read, and if you think about it, it gets the design points, right, the structural design across very nicely. But make no mistake, you actually don't want your software dealing with strings. Whether it's MongoDB or, frankly, any other database, you want to interact with your persister using high-fidelity types, not big strings with white space and carriage returns and quotes. So to that end, and just very briefly on this, in Mongo, the drivers for each language that can connect to it will represent those documents in a language-native form most appropriate for the language. So in Java, when you ask for a document, you get back a map. In Python, when you ask for it, you get back a dictionary. And inside of those very high-fidelity types, you find actual objects like dates. You do not find strings with white space and things that need to have the double quotes escaped and all of that. Another important note is that as we go forward, we're going to be using the query functionality really to kill two birds with one stone. We're going to use queries to reveal the shapes of the documents that we find, and also just to look at a bit of the MongoDB query language itself. Important to note that in Mongo, documents go in the same way they come out. This is another different design paradigm from RDBMS, where the read side of an operation, for example, like an 8-way join, right, is very different than the set of insert statements, maybe some of them in a loop, required for the right side of that kind of operation. So in summary, traditional schema design, what are some of the things that we find? We find a lot of rectangles, and they're pretty much all shaped the same way within the tables. And it's largely because the design goals and constraints of the legacy engines are heavily influenced by the data being put into them. Overall, those platforms are necessarily focused on physical representation. And for example, and the truth is a lot of the following types have been conflated in these engines over the years, the legacy existence of things like car, varchar, text, clob, all these things to represent strings suggests a very strong coupling to byte-wise storage concerns. In the document schema design, we think about things differently. You want to think more about business entities. You'll want to think about your data moving in and out as objects. Now, that analogy is not and should not be 100% tight and correct. Because remember, we're only dealing with data. This is not an object database with state and behaviors and bindings and mappings and all that. It's just structures of lists of structures, and also no compile time binding here. Very, very important to be able to get the data in and out of the system in a rich way without being forced to compile the code around it. What better way then to take a look at what all this means by rather than excuse me, by diving right into a problem and the example. And what we're going to do today is use a library management application. The good news is most people understand how a library and books and publishers work, and also it happens to have a couple of good relationships on a one-to-one and one-to-n basis that will allow us to explore some of the schema design and code design options around it. So, to make things a little more interesting, we're going to try to capture the requirements for this schema in the form of questions. These are the kinds of questions that ostensibly the app, or that the code layer, probably even just below, the data access layer, if you will, needs to ask the database. This is useful, again, because it helps us keep our eye on the software layer above the database. So imagine a user, a patron, is going to go into the library and check out some books. First thing the librarian is going to want to do is confirm his address. And we're about 15 seconds into our design, and so here's what we do. The very first thing we experiment with is something that looks like this. We've got two collections here, patrons and addresses. You'll notice that, but again, this is the MongoDB command line interface view of a query, where we're looking up on underscore IDs. We'll come back to what that means in just a moment. There's a common key, Joe, here that bridges across the two collections. And frankly, even in the RDBMS space, before you started to understand truly the relationships between two tables, you might approach it in this way, and that's fine too. Now, one of the things I do want to introduce very early on is that there's a list of favorite genres that's been set up here in the patrons table, collection. So I'm guilty of my own, there it is, prophecy fulfilled. That favorite genres element is a list of strings. It is not a semicolon delimited string or commas or any other sort of encoding. It is a nice, discrete list of strings. Each element is addressable and queryable and updatable via the dot path. I can even replace the whole list if I want. And should we require it, I can actually index on entries in that field. But we're going to get to that a little further on, so let's not get too far ahead of ourselves. So after this is done as our first shot, the question becomes, can we do better? And I think we can. So what have we done here? We've moved the address into the patrons collection. Now, now only one query is necessary. I go for the ID and I can pull everything back. Now, what's important to note is that I've treated the address like an object. I haven't flattened everything out into address underscore street, address underscore city, address underscore state, etc. Certainly, you probably, for this sort of thing, wouldn't want to leave city, state, and street without a namespace around them, right? You wouldn't just put city as a peer to favorite genres because it kind of loses its association with the rest of the address. But we didn't flatten it all out. We're going to see how this use of substructure in just a few slides is going to be extremely powerful. Now, usually it's at this point where, as people start to see where we're going with this and creating documents that are ever larger and got complex structures in them, they fear that there will be this massive hit on the network and the database to pull everything across. And the answer is that's not true. With the concept of projection in MongoDB, you don't have to effectively select star. You can ask for just the fields that you want. This operation is, of course, processed on the server side and is efficient. So it's not, there's no trickery here with dragging all the content across the net to your client and then throwing away 90% of it. It's being processed server side. Now, what's very interesting here, as a result, is that you can pick up both an entire structure, as we see in this first example on the top, of address, or if we really want to, we can dive down using dot notation to pick up individual pieces of a substructure. Very, very powerful stuff. And in fact, it's the first form where you're able to get at the entire substructure of a document. We'll see the power of how that mates with some of your software in just a moment. So in summary, one-to-one relationships. There's a lot of belongs to relationships that are out there, and these are often embedded. Clearly, you're going to get great read performance out of this because one query hits against a set of bytes that are stored, and it's going to be vended back without a great deal of effort on the part of the database engine itself. But perhaps in a more subtle way, what's more important is that simple things are kept simple. And because you don't have to worry about what it means to deal with favorite genres as potentially a foreign table with foreign key management, or in the absence of that, just sort of encoding it with semicolons and such. This gives you time to actually look at the harder parts of your schema design and be excellent there. So let's move on now. We're on to we're still early on in our design. Now our business requirements have changed. And maybe we kind of knew this within seconds of the first attempt, but now we know that people may have more than one address. We also are going to acknowledge, again, legacy practices, where in the old days we might say, let's just assume they have two addresses, address 1 and address 2. Well, that's great until somebody has a requirement for address 3. And we want to avoid that, and we're going to not repeat it. So how do we do this in MongoDB? Well, we can model addresses as an array. So that was pretty easy. There's no need to create a new table or set up the foreign keys or do key management. What we see here on this slide is really now the combination of substructure lists all brought together. And one of the things, obviously, that you can do is add to this list. You can subtract it. And as I said before, everything in here is indexable and individually addressable. To a certain degree, for these kinds of relationships, it almost takes longer to describe what you're trying to put together in words than it does to actually code it. And to make this information available to your application it is just as easy as well. Going back to the Java and the Python examples, now if I asked for everything associated with patron Bob, I would get back a map that has a field in it called addresses. Addresses would be a list of maps of which I could extract street and city. That's very powerful stuff. Now, there is, of course, the issue of, well, what happened 20 minutes ago when I put in the initial address? So we're starting to see here the first bits of power of the dynamic schema capability of MongoDB. And that is that each document can contain a different set of fields in it, and that it is up to the code to figure out how to mediate between the two. Now, there are two aspects to dealing with this issue. Okay, the first is, as I just mentioned, in our paradigm, the software up on top is responsible ultimately for doing not only just sort of these schema level issues, but business validation and verification. But also, there's a migration strategy. And keeping in line with the theme of MongoDB offering choices, there are several things that you might be able to do when faced with this sort of thing. So the first is you can, and this is what we tend to do now in traditional databases, is we're just going to migrate all the documents. Okay, so, and that's 5 lines worth of JavaScript that basically will say iterate over the collection. If address exists, go create an array called addresses, create it with length 1, then delete the old fields called address. There's another technique called migrate on demand. This is where, as the content is accessed, what is nominally a read operation becomes a read with potential update. And that is, the code says, as I'm trying to put, this is your production code, this is not a utility that you run. If addresses exists, then do what I just described before that the utility was performing, and that is to create an array, addresses of unit 1, and then kill the old record. This is actually not a bad way to do things if your design, your functional, non-functional requirements permit you to take a write hit in the middle of what is nominally a read operation, and that's fine. Of course, you could always just leave it alone. There's really no reason why, if you've got a good code layer on top, you can't have both living there. And in fact, for certain more complicated kinds of structures or legacy archiving reasons, you may not want to change the old data. You may actually want to have it live on in the form that was first persisted. And so, in a very interesting way, Mongo provides you with the capability to continuously move forward with your data. And as long as you're always thinking code and schema together as a unit, this allows you, in many cases, to bypass having separate archiving and warehousing kind of environments that are there to pick up the old shapes of data that no longer can function properly within the online ODS. We're not going to talk about physical scaling a lot today. Today's more about schema design, but know as a footnote that MongoDB's technical architecture, its ability to scale, allows these sort of things to happen. So you can start small, grow large, and in addition to having documents with different shapes, you can have millions and then billions of these documents and still have good performance. Now, this is something that I think is very useful and interesting. I mentioned before about the power of substructure. Substructures really allow your schema to harmonize with the software around it. In this example, we're trying to pull out address. It's sort of a mix of some of the things I described before. If address is not there in the collection, it'll try to go get the list, and then it plucks out just the first one. It then calls a function called do something with one address. Now, what's really, really powerful is later on, if I say I now want to add, for example, region to the address or any other thing, none of this code has to change. The only thing that has to change is the actual content in the field in the database, which is obvious. And then somewhere deep inside of do something with one address, it may begin to look at another field which may or may not be set, called region. Now, the reason that's incredibly powerful is the queries, the basic design of your solution that wanted to pull address does not have to be exhaustively checked to now pull one more field. You just pull the address, and only at the point where some of the substructures are actually going to be used does it have to change. So it allows you to flow data throughout your system very, very efficiently without a lot of change. That's very, very powerful stuff. All right, let's now ask some more questions. We're going to now look at publishers and books. We're expanding now out to the third entity, and we're going to shamelessly plug the MongoDB book since we have your attention. What you'll note here is that we have two authors in the book. Everything else is pretty much straightforward. So how would we model up a book in MongoDB? Well, here's our first crack at it. We've got some titles, we've got some authors, the published date. We've chosen here, now perhaps a little controversially, to embed publisher right inside the book. Now, at first, this probably causes a lot of discord for traditional relational development because the book and the publisher is not as strong a one-to-one belongs to relationship as what we saw before, for example, like with favorite genres. However, just for the moment, let's explore this because we want to capture, for example, a performance benefit of being able to read all this out. We also know that largely, books and the publisher for a book is immutable. In other words, once a book is published, the publisher doesn't change. To be fair, Maybe some of the reference data around it might change. Like, for example, founded 1980, maybe that's wrong. It has to change to 1979. But those kind of operations are few and infrequent. And so what we're doing here in this kind of a design is we're trading off the performance for the duplication of data, but acknowledging the data doesn't change very often, so you don't have an ongoing problem of data integrity. And of course, if you were following along with my enthusiasm about substructure, here's maybe crack number 2 that we want to take here, and that is do not create author names as basically formatted strings, first name, space, last name. You'll know when your schemas are rich and when they're powerful, when you don't see white spaces. The name O'Reilly Media aside, that's its full name. But first name, last name, middle name, salutation, phone numbers, none of those things should ever have a white space in them, because you always want to be able to compose them as, A, you want to be able to compose the individual bits without breaking apart some of the formatting. Number 2, it allows you to take advantage of binding code to substructure. All right, so in summary, what did we see now with our book with embedded publisher? You're going to get very high performance on the read for that book. We've talked about accepting the data duplication there. And interestingly enough, if you create an index on the publisher name, which you can do because, as I mentioned before, every field in a document is indexable. Then you can look up the books given a publisher name, and in fact you can call a distinct on that as well and get very quickly a list of all the potential publishers. But maybe that's not so good. Maybe we actually do find that publisher information changes. So let's move on. Let's give it a crack here as a separate entity. So we're going to set up a different publishers table here. It's very simple. We're going to assign the underscore IDs here. There is a requirement in MongoDB that every document have a unique underscore ID field. It's not important for today to get into what is actually an advanced topic of underscore ID construction. You should note 2 things. If you don't have one, if you do an insert without one, Mongo will create one for you. And here's a bit of a teaser. That underscore ID does not have to be a string or a number or a scalar at all. It can be a multi-field substructure itself. As long as the components, when all put together as bits, if you will, come out to be a unique value. And notice also how the one-to-one relationship of locations carried over nicely into here, because that truly is something that is a convenient and simple one-to-one belongs to relationship. So how do we now get the combination of the book and the publisher? Well, we do it in this way. We do 2 queries. Now, this isn't the end of the world. This is what we call linking. And the idea is, instead of composing a select statement with a join, and then writing code or otherwise configuring your ORM to break apart the result of that join so that you get back a set of books and just one publisher for each book, you're doing the work yourself. The code layer deals directly with the database to put the information together. Now, this example shows a one-to-one. You're looking for one book. The one book is going to have the one publisher. So let's say that's easy. The really snazzy thing now becomes, what if I've got multiple books? And here's where we start to get a little fancier. I didn't specify all the criteria here, but what we're basically asserting is that what I'm going to do is first find all the books that are important to me based on whatever criteria it might be. As I'm doing that, I'm pulling out the publisher name. I'm capturing that uniquely in a map. So for each record that I fetch, if the publisher is A, B, B, C, C, I only am capturing A, B, and C as unique values in this map in my code. I then interpret that as a list and turn around in the bottom part of this slide, and I call publishers using the $in operator on ID. Now, this is efficient because that's the primary key on the publishers, and whether the list is 1 long or 10,000 long, or potentially even 100,000 long, it will still be passed to the database, and in an efficient way, all that material will be collected. This is effectively what you would see in your code to do a multi-row join to a different table. Now, here is something that is interesting vis-a-vis the network. For relatively low numbers of publishers with respect to books, which there probably are, coupled with a good amount of publisher information that you want to pull back, the network hit here is going to be lower with this logic. It's going to be lower than a traditional join. And the reason is, if I was to traditionally join books and publishers together, if I've got, let's say, 25 or 100 books for each publisher, every single row is going to have the publisher information repeated over and over and over again. That's all going to get dragged across the wire. By taking control in your code, you're only pulling the information for that publisher once. And then, of course, on your client side, then you're going to assemble it as you need. So there are times where, especially as your data grows and cardinality shifts, your code will be in a better position to manage that than just blindly creating giant rectangles and then decomposing them as we've done for the past 40 years. All right, let's move on to another kind of question here. Now, we've actually already seen a way to do this. We can find on the books collection with a publisher name. But is there another way? Because with Mongo, it's all about looking at and exploring the different ways to do something. This time, however, we're showing you a counterexample. We're showing you something not to do in MongoDB. Arrays, these lists, clearly very useful in MongoDB. But beware of the temptation to treat them as rows, because they're not. Arrays should be growing, and not without a reasonable bound. So, for example, you wouldn't carry system of record customer transactions as an array inside of customer. It's tempting to do so, but it's not a good idea. I will say that you might, for the purposes of speed at scale, duplicate the last 3 transactions as an array inside the customer record. Just holding on to the last 3, and then a different collection entirely is handling the full list. You can mix and match. Arguably, it's very easy to do that because, coming back to before, the power of arrays and substructures, you're just moving from one to the other and managing the size. From an underlying technology basis, truly this is less of an issue now with our Wired Tiger storage engine that's available in MongoDB 3.0, but you should still be mindful of creating arrays that grow without bounds. So who are the authors for GIF and book? Well, we've seen that the good news is that an increasing number of questions can be efficiently answered by the existing set of entities. This holds true for authors, but suppose we want a little more detail on the author. So let's go ahead and try to put together an author's collection. Now, what do we see here? We're using some fancier code, and the reason is we're still doing the 2-step process, 2 queries to get the information. However, we have to dig into that author's list in order to pull out the unique IDs to turn around and call to get information in the author's table. But it is effectively the same design pattern, which is find the things that you need, extract the underscore IDs that are important to you, and then turn around and use an in operator to go fetch them from the other collection. Of course, as I mentioned before, you can use projections throughout here. So it's not a matter of dragging all the information. If you just wanted to find the author's last name, you could do that efficiently as well. And then you have a very, very small footprint hit on the network. We also, just for clarity, you'll notice that we've kept first and last name inside the author's list in books, even though we do now have an author's collection. Not required. It's there perhaps for speed if we want to do the quick lookups. There is a data integrity issue. Yes, there is. But in general, these kinds of pieces of data are immutable. And so we may make that decision to do the speed versus lookup trade-off. Certainly, if we really wanted to be strict about it, we could abandon first name and last name and always go to the linked authors table to find those names. Again, and it's a little, maybe a little harder to see on this slide, but substructure rules here. The substructure that you could extract out of authors is the same amount of material that you could extract out of the names down, in books, is the same that you could extract out of the author's collection. Getting it a little more complicated now, we're going to now really see a trade-off between performance and speed, which is now we're asking the other question, which is, what are all the books an author has written? So typically, if you know that your material is largely immutable and you want to have speed and performance trade-offs, you'll doubly link books to authors and authors to books. Again, the data is somewhat static, so referential integrity is not as much of a real operational issue as the benefits you get from performance. Now, we've kept title in the structure, again, just in case we want to do a very quick lookup on authors on a page and immediately splash all of the books that they've written without having to do that second query. And again, as a footnote, that second query is largely analogous to what a traditional RDBMS would have to do in terms of a join, right? It still has to do some amount of work to bring the tables together, bring the keys together, construct the Cartesian product, and vend it out. It's a lot simpler if you can get that down to a single lookup and just vend the bytes. But if we so desired, we could have, as I mentioned before, we could have that books array in the authors collection simply be a list of IDs into the books table collection. See, I'm doing it all the time now. And use the two-query approach. It really is a choice that's up to you. Or you could use indexes. Now, one of the great things about MongoDB is that all elements in the structures are indexable. So typically, you wouldn't think of this, but you can actually create an index on those underscore IDs inside the authors field directly, and that will become now efficient. So if I've got the book and I do the lookup, I can find directly from within the books table all the places where Christina, who's X12, may exist. And then I can turn around and do a fast lookup into the books on that. It will take more than 0 millis. I apologize, when I ran this on my machine, I ran it twice and it had cached it the second time. The point being that it did find it using a high-performance query and delivered the information back in very, very quick time. In summary, embedding versus or embedding and linking. Embedding gives you terrific read performance, suitable for your front pages, pre-ags, complicated structures, right? Things where it's not just saying select first name and last name from employee. That's not reality. You could also imagine that inserts might be a little slower than linking. If you've got very high performance data that's kind of smallish, rewriting, for example, the publisher material every time might slow down things a bit. And of course, you have to maintain data integrity across the collections. Linking. Linking, in summary, is it's you doing the work yourself that historically would be performed by the RDBMS. So that is work, but it's not necessarily more work than a traditional approach. Overall, you may be writing a little more code, but the overall amount of processing that has to be done is going to end up being roughly the same, sometimes faster, as we saw before with respect to publishers and authors. All right, now we're actually getting into the interesting and really specialized parts of MongoDB. Suppose the library wants to have, they're going to add value, and they're going to have some book clubs, enhance author information with bespoke information. Got a couple of challenges trying to do this. The first is the book club or clubs are operating independently from the people who are building the system we're talking about today. We don't know in advance what the book club is going to add. And each author may have different information created by a different member of the book club. So how do we capture the requirements on that? And the answer is we don't. What instead we do is this. This is an exciting and useful part and powerful part of MongoDB. You do not have to come up with user-defined column 1, column 2, any of that noise. You can see here that Christina and Mike have got very different substructures inside their personal data field. This kind of design concept we call polymorphism, and that is the variation of shape from document to document within the same collection. Now, the library application logic here is only looking for a field called personal data. That it knows about. However, once it extracts that field, actions will be taken dynamically based on the shape and the type in the substructure. For example, it's a very straightforward exercise to recursively walk that structure and construct a panel in a GUI. If you are using something like AngularJS in the main stack, which is MongoDB, Express, Angular, and Node.js, this becomes really, really easy to do. There's no need to use XML or blobs or serialized objects. It's all native MongoDB with rich types, and the documents are represented in the form most easily and natively manipulated by the language that you're using. And yes, every field in here is still queryable, and if so desired, indexable. Polymorphism itself is so strong a concept that it's worth an extra slide. So independent, we're going to sidestep library for just a moment here. Consider a collection of events. Now, we've taken out _ID here just to give you a little more space, but the concept is the same as what we saw before. Type, TS, and data as field names are well known. The information architecture is always going to use them. There's probably an index on type and maybe timestamp as well. But the data field, the contents of the data field are specialized for each type. Again, there's no need for complex tables or blobs. It's very easily extensible for new types that we don't know about today that can just live in the collection and continue to grow, be efficiently indexed, and queried. This model that you see here, it extends to many things: products, transactions, actors in a system. If you think about your data in terms of these kind of entities, coupled with polymorphism, you'll discover that you probably only need a handful of entities, and that you get a very long way in terms of flexibly using data in this fashion, describing it in this fashion, and the software around it. And because of this design approach, rarely will you see a MongoDB database with hundreds of collections in it, because it's not necessary. All right, we're going to touch upon one last little bit of capability here, and that is along the lines of faceted search or tagging in general. And we're interested now in finding out about books about databases as the specific example. And how can we set this up? Well, here's a first crack at it. We'll just create, and I took out some of the other fields here just for a little bit of clarity. But the categories field now contains 3 tags: MongoDB, databases, and programming. And I can do a find on that list for databases. I can, this is, by the way, okay to do. Typically, I don't have a lot of tags, and I don't change, they don't increase without bound. So it's well represented as an array. Feels very much like a belongs to one-to-one relationship. But the good news, again, is that I can do a performant lookup on that. And if it becomes so important, I can produce an index on categories and get index-optimized searches into that. Very straightforward way of dealing with it. There's another capability in Mongo called a regex, regular expression lookup. And what we might choose to do instead is actually define a hierarchy. Now, what we've done here is set up category as a string. And we're deliberately encoding the string with slashes, right? There's a path encoding in here. The idea is we want to exploit the regular expression lookup capability in MongoDB to find components of that path. And as long as we left anchor it, it will use the left anchor is the little upward, the caret in front of the P to say anchor to the left-hand side of the string. This will allow me to use the index and category, and from the top, dive as deep down through the hierarchy as I want to get all the matches. Obviously, this particular regex would pick up programming databases, MongoDB, Postgres, Oracle, etc. There's a downside to this, of course, and that is when the category gets changed, your documents have to be recategorized. But this isn't a MongoDB problem per se, it's a general information architecture problem. So, let's summarize. Schema design, is different in MongoDB. Well, it is, but at really the core, the basic design principles stay the same. And I might even assert that because it allows you to focus on really your core entities, like product, transaction, book, actor, etc., and not get distracted with some of the other one-to-one or one-to-n things that have to hang off the side. It allows you to more easily design some of the solutions that you need to create. It's important, number two, to look at how the application is going to be dealing with the data. This is, again, not new. This is Software Engineering 101. We should have been doing this all along. It's just over time, we've gotten a little soft in terms of acknowledging that the system is holistic, and instead we focus on the database, and then a miracle happens, and then the application is doing something on top. MongoDB thrives. Your solutions will thrive when it's well harmonized with your code. Clearly, those belong to one-to-one relationships. Fantastic to model inside of MongoDB. Frees up a lot of time for you. Use substructure. Right? Identify ways to break things apart. Imagine if you had a real estate app with buyer name, seller name, lawyer name, guarantor name, executor name, all these kind of components that would be, or fields that would be important in your schema. Now you wanted to add nickname in there. Traditionally, you'd have to go back everywhere to every query and add nickname in to drag it out. Here, you just add it into the substructure. All your queries that were picking up names will continue to pick them up, and your code can adjust accordingly. And of course, be sensitive to the fact that it may not be there, and perhaps substitute a default value. Lastly, be polymorphic. Do not underestimate the power of that. It's one of the great things that you can take advantage of in MongoDB. And truly understand that in 2015, you need to evolve your schema as the requirements change. Very few of the solutions we're trying to build now will be requirements complete in the kind of time frames that we're looking for successful delivery. So with that, I see it's about 10 minutes to the top of the hour, so I think, there we go. So now we're on to questions and answers, and I'm going to switch into my mode here. Look at what's going on in the chat room. Okay, so a thing that popped to the top. Is it possible to migrate on demand when using the aggregation framework? So the aggregation framework, this is MongoDB's version of group by, if you will. And the answer is it is assuming that the migrate on demand code bits are going to be called before your new aggregations are called. This is probably more of a software design issue rather than a MongoDB functionality issue. But clearly, if you want to go down the migrate on demand route, you're already setting yourself up for a tidy piece of software that's got to understand a bunch of different states and perhaps a bunch of different logic paths. Number two, this is an easy one, how to create an index. You ensure the index. I jumped over that very quickly, but back when we were talking about books and authors, there was an ensure index function call that said, using .path notation to describe the way I want to get into a document, create an index either ascending or descending on that. Of course, other options apply, like is it sparse, is it unique, etc. Very straightforward to do. In that case, we don't need to, I don't know, the thing is there is a question, how do I do proper lookup with criteria on both books and publishers' collections? Like to about downloading all the data that does not match at all. Thanks. Okay, so there are going to be times when mathematically the kind of cardinality analysis that you're going to want to perform to understand which side of a join, by the way, this is in a multi-way join that obviously even gets even more complicated, where what traditional database engines have a 40-year jump on us doing is figuring out who's the smaller one to filter on first to then get the larger, and then to go after its smaller cousin, right? You always want to get the smallest cardinality first, and then in decreasing order. You're going to have to do that yourself in MongoDB, but most of the time, these kind of issues are either A, kind of implicit, like you're going to have more positions than transactions, you're going to have more books than publishers. B, and we didn't cover it today, not to be underestimated, is there are times when you shouldn't be going to the database at all. Like, for example, currency codes, country codes, things like that. You should never be looking those things up. Those should be at the top of the application. You hit the database, you pull the codes, you put them in a hash map, you're done, right? If you really are concerned that a country is going to change its code while your application is running, you can put, now we don't have triggers, but you can do effectively the same thing with Mongo by tailing the op log. And you can watch for changes on a particular thing. But in general, there's going to be a lot of really static data that's simply not worthwhile to force into the query of a database engine. There's another question here. What is the impact on performance for a search on a category array versus title? So the answer is they are effectively the same. The longer the category array is, it's simply the larger number of unique elements in the index, but that's the same as if I had a whole lot of titles. This is why, you want to make sure that your arrays don't grow without bounds, because as you do that, you're changing the indexing structure all the time. And B, you can run into unanticipated problems when you start adding and deleting tens or hundreds of these things at a time. For example, if you start treating it like a delete statement, where you're going to delete hundreds of things out of an array, that's going to force hundreds of changes into the indexing structure. But for relatively static or slowly growing arrays, the performance on the lookup of that array is going to be the same as a lookup on a regular string. How do you so there's some questions on integrating to a normal DB. Actually, there are several questions vis-a-vis migration and integration to normal DBs. I'll simply say that there's a whole webinar I did like last month entitled Migrating from RDBMS to MongoDB. You can look that up on our mongodb.com site, and there's a lot of information there both on the techniques and some of the tools that you can use. Let's see, what else do we have here? My team here is answering some of these as fast as they pop up, so I'm trying to find one that hasn't come up. Okay, so here's one that I'm happy to answer. The question is, what's your take on Spring Mongo support? Is it worth using it, or is it better to stick to using the Java driver directly? So Spring, it works okay. Morphia, which is a POJO mapping framework that was built by a Mongo employee, although it's not part of the official release, is even better. But in my 27 years on the other side of the table, including being chief architect at the iBank at JP Morgan Chase and at Bear Stearns before that, I am a very, very big fan of keeping your POJOs separated from your data access layer, which is separate from your persisted form. Inevitably, I find that these frameworks work for a little while, and then there's something that they do, or I should say something that they don't do, that will end up getting in your way. Mongo truly is a little better at this than legacy things like Hibernate on top of RDBMS, precisely because MongoDB isn't afraid of lists. Right? It doesn't have to unwind gigantic Cartesian products in result sets in order to come back with lists of objects. But that said, there's always going to be something on like the 6th month of your development cycle that comes back and hits you with these things. So my personal preference is just go with the driver. Okay. Let's see. We've got, let me scroll here. And cover that, IDs. Okay. I have a question. You explained that querying on IDs contained in the list is performant as the ID of the primary key. That's true. How performant would a query on a non-ID property or the property? Oh, okay. So how performant would a query on a non-ID property be? The answer is you're going to table scan unless you create an index on it. And coming back to what I mentioned before, any field that you saw in any one of those slides is indexable. I might also add that if you say that they're sparsely indexable, you get pretty good trade-offs between the hit you're going to take for writing the index and doing reads. Particularly in this polymorphic kind of world, you shouldn't be afraid about creating more indexes than you otherwise would, because only those documents expressing those fields will have an index put on them. You don't have to worry about a whole lot of null columns and some of the optimizations that have to be taken to ensure that writing something that's got 16 or 18 indexes on it is going to perform terribly. Because if you've got nice cardinality and a good distribution of the kinds of things you're indexing on, you're really only perhaps touching out of those 18, I'm just picking a number, let's use 20 as a better round number. You might only be hitting the indexes of 4, but it's a different 4 for each kind of type that you're putting into that collection. Is there a cap on how much data can be stored in a document? The answer is 16 megabytes. A document can be no longer than 16 megabytes. If you want to go bigger than that, there's a capability in Mongo called GridFS, which allows you to store an arbitrary amount of bytes as a stream inside of a collection. And behind the scenes, it's chunking it up and kind of doing what you think it does to spread that across multiple documents. What are the available drivers to connect MongoDB? Yeah, a lot of sort of upstack stuff here. There are drivers for Java, C, C++, C#, Python, Java, Ruby, and in the community, I forgot one or two, and Node.js. In the community, there's dozens more. There's R, SAS, all kinds of things are supported. And by the way, there's good support for those because the scientific and research community depends on them very heavily. Let's go down to here, one to deeply. Can't answer that very fast. Can you store the results of an aggregate query? Okay, so we're almost out of time. I'm going to take two more questions. So somebody has identified the bulk API. Thank you very much. The bulk API is a higher performance way of inserting a bunch of things into Mongo at once instead of just doing insert in a loop. The question is, do I recommend using that over doing the updates in a loop? The answer is absolutely. Truth in lending, it is not an atomic operation. It's easy to be fooled into thinking that doing that bulk update will treat things as if there was a start trends and end trends around it. It won't. But especially for smallish documents like 1K or smaller, and you're inserting hundreds or thousands of these things, it's much, much more efficient to use the bulk API. Last question I'll take here, it's kind of an interesting one, is can you store the results of an aggregate query in a GridFS record? Well, you can store the results of an aggregate query in another collection using the $out operator. I believe that even if you were going to take the answer is you can definitely do this by taking the results, bringing them back into your client code, and constructing what you're going to stick into GridFS and then sticking it back in. The degree to which you have an ag query that's going to produce more than something that would exceed a 16 megabyte footprint, that's a pretty big ag. And so I'd sort of be interested in understanding a little bit more about the use case around something that creates such an enormous aggregate on the outside. But the answer is, in code, you can do anything. I know it sounds a little sort of escapist, but that's the truth. All right, so we're actually at the top of the hour. I do want to thank you very much for attending the webinar today. I hope it gave you some amount of insight into the way we think about things here at MongoDB, and that it'll give you some clues into what you're going to face in your own design efforts. Remember, you can always reach out to us at MongoDB for some guidance. So with that, code well and be well.